Welcome back to our heat transfer class, where we're delving deeper into the one-dimensional, steady-state heat conduction. This video was made with the support of InnoEnergy. The topic of one-dimensional steady-state conduction is divided in several lessons. There is at least one video for each lesson. In this video, we will apply the knowledge acquired in the previous lessons. The problem to be solved is the calculation of temperatures and heat transfer rates for an electronic chip with a heatsink. For keeping a one-dimensional conduction, we will consider the sides of the set to be insulated. The fluid in both sides have different temperatures and convection coefficients. Fins are cylinders of diameter df and length lf. The chip and heatsink have a square cross-section of side w. Data for solving the exercise are given in the table. The heat generated in the electronic chip is divided into two heat streams, Q1 and Q2. We will use the concept of thermal resistance for calculating T1, T2, Q1 and Q2. For simplification, we can consider the heatsink as a single thermal resistance. First of all, we apply the conservation equation, so that the heat generated in the chip is Q1 plus Q2. The heat generated is 100 watts. The thermal resistance R2 is the convection resistance of a plane wall. The calculation of R1 is more complex. For one fin, the perimeter is pi times the diameter, and the cross-sectional area that of a cylinder of diameter df. The Biot number is small enough to accept the one-dimensional conduction hypothesis. Before calculating fin's efficiency, we must calculate the MF parameter. The formula for the efficiency is the one for fins with convection in the tip. The prime area is the cross-sectional area of the heat sink minus the cross-sectional area of a fin multiplied by the number of fins. The area of one fin is the lateral area of the cylinder plus the tip area. With all these data, the value of R1 can be calculated. Now, it is time to calculate the temperature distribution in the electronic chip. For the application of the Fourier's law and the diffusion equation in the chip, we need to define a z-axis. For the application of the Fourier's law, we consider L components of the heat transfer rate to be written in the direction of the z-axis. The diffusion equation for the chip with internal heat generation can be integrated twice. The boundary conditions are the temperatures at both sides. C2 is the temperature for Z equal to 0. With the second boundary condition we can find C1 and, finally, the temperature distribution. And from the temperature distribution, the expression of the temperature derivative. Now, we can apply the Fourier's law in the chip surfaces. And the temperature difference divided by the thermal resistance. With the derivative of T at Z equal to 0. And the derivative of T at Z equal to LC. We have a system of equations that allows calculate T1 and T2. Once temperatures are known, we can calculate Q1 and Q2 and check the conservation equation. For drawing the temperature distribution, we will use the z-axis. For the chip, we use the solution of the diffusion equation for a plane wall with heat generation. T0 can be calculated using T1, Q1 and the thermal resistance of the plane wall of the heatsink. With the formula of the fin with convection in the tip, T0 and the value of MF calculated at the beginning of the exercise, and making a change of variable. We can calculate the temperature distribution along the whole system. You can see the second-order polynomial curve for the chip. The linear line for the base of the heatsink, and the nonlinear curve for the fin. For the maximum temperature, the derivative of T must be 0. Therefore, the exact place of the maximum temperature can be calculated. You can see that because the asymmetry of the boundary conditions, Zmax is not in the middle of the chip.